This is just going to be a quick update of my current progression of my Something Awesome project. To give a quick refresh of what the project is to create a virtual blur kit that implants itself underneath a current running operating system as a hypervisor, which intercepts all the communications between the userland kernel and also hardware by fast interrupts and basically all the interrupts. This is just a quick and simple demonstration, quick and simple update. As I discussed earlier in the posts in x86, how I've shifted. Due to a lot of limitations of x86, I shifted to ARM, just to see if that's a viable option. But first things first, I should actually explain why x86 wasn't a viable option. The issues with x86. For what I want, I need to be able to create a hypervisor. To create a hypervisor and run it, basically I would either have to create a virtual machine. In x86 is weird because it actually creates the virtual machine, the host as a process, which I find funny. And basically you can then just simply switch between the virtual machines in the process. It's all done in hardware, which is quite nice, but it's like, yeah, so in a proper Type 1 hypervisor, the booting up process, it would store it will first create a single process, the hypervisor, and then the hypervisor deals with the VMs, which is another process inside the hypervisor, which is cool. But in this context, but the only way you can do that for a current running operating system is to actually initialize that at boot up. And basically then copy the current running operating system before it gets copied into memory, intercept that, create the virtual machine, and then put the virtual machine, copy the kernel code of the executor into the address space of that virtual machine you created. And the only way you can do that is if you modify the boot code. That's where we run into our first issue. You have to modify the boot code. And in modern x86 machines, there's a nice little thing that screws you over called secure boot. It's not screws you over, it's a good thing, but as a security engineer, or as a attacker, it's a pain in your bloody ass. Because basically, it checks if any of the part of the initial boot code has been modified. Basically the part of the code which is mapping in the kernel. And that's basically exactly the point where we need to have our context switch, so we can, instead of mapping into the kernel, we map into our own virtual machine's kernel address space. So basically how it does it is it does a quick, it does it one of two ways. It does a quick checksum or a hash of the boot code and compares it to a table of accepted hashes. If it doesn't accept the boot code and just stops. This is usually done by the BIOS itself, or in terms of later ones, it's the Intel, the Intel execution engine or something like that, which actually is the thing that houses the TXT. It runs on the theoretical ring -3, but I will discuss that later. With the SKU because of SKU, we can't do that. But obviously, this can actually be disabled in BIOS, so it's not too much of an issue. We can get around that, but I wanted to attack. I want this to actually be a valid attack and not just proof of concept type of deal. So I was like, eh. Then the next part is we can technically still get away with it, as we can see here. We still technically get around it by simply unmapping the kernel and then copying it into as the kernel, copying itself into a virtual machine, then running that, and then just killing itself. But goddamn, that's not a simple feat, not by a long shot. So then we move to our next one. That's not going to happen because that can technically happen after the thing, but like no. The next one is the Trusted Execution Technology, TXT. Basically, this creates a little region of memory which is unaccessible by anything on any execution level, with the exception of the firmware running on the Trusted Execution Technology. They're the only ones can access this information and the process which they initiate. Long story short, it's basically it can be used in a lot of circumstances. It's usually used for crypto stuff to store secure keys because of basically you can throw in a variable. It basically acts like a miniature kernel. You can throw in a variable in this artificial kernel. Nothing can touch it, and blah blah. But in this case, because it actually has rights over everything in the system. Like, it can see everything in the system. You can reduce that, but by definition, it has rights over everything. It can actually it itself does the checksum on the boot up, and also does the check on the any running processes to see if any of it has been modified. So in this case, it can, in most cases, they implement the big virtual machine manufacturers like VMware uses this technology to implement a way to check if their hypervisor has been modified in any way, any sort of way. And if it has, it kills the hypervisor and goes no. Actually, it's a little fun because this uses the Intel Engine. Actually, I think it's just called, or Intel Management Engine. That's it. Which actually is itself like a super complicated thing, which runs its own operating system, and it actually creates backdoor. It's an actual backdoor Intel's created to allow like sysadmins to do all fancy stuff, like actually just stop execution of all the computers, delete the operating system, and put their own in. It's actually a really cool attack vector, but I'm not going to go into that. The next issue is not having the virtual extension enabled. In x86, you have to physically enable it by BIOS. So the Intel Engine, and before that, I think it's RingNate 2, if I remember correctly, the Intel Management, the SMM. So yeah. It's also, without the extensions, you have to do basically create a parallelized operating system, so you basically have to replace any instruction which doesn't cause a fault. Privileged instructions that don't cause faults. There's a few, and basically that's just a history in x86 virtualization. It's a fun topic, and basically without that, basically you have to rewrite all code to cause traps. Not doing that takes forever. No, that's not integrity. That was like, I think there's only one company that managed to successfully do it, and that was VMware. And by God, that was a hell of a task on their behalf. Also, just x86 in general is a fairly complicated hack together type of system. It hasn't been designed it, and because of it is a very complicated system, there's not very many strong hardware emulators for it, so it makes it very difficult for testing and that stuff. I have most likely I have to run on hardware, and testing on just pure hardware without having unlike other systems, there's no UART port or something that you can just tap yourself into and listen to push out debugging information. It's hard. So yeah. So let's see how well ARM fares. Okay, first I should explain how, before I get into the nitty-gritties, I'm going to explain how x86 virtualization works. It's quite fun. Basically, it's simply in the normal... Okay, let's call this here VMX non-root ring. It's ring 0 to 3. Technically, this is called the base. This is non-root. The non-root creates, this actually is probably not a good example. Initially, when the device boots up, let's use this. Initially, when the device boots up, it goes into ring 0. Ring 0 then can create, using Intel special instructions, basically a virtual machine. It itself, ring 0, becomes VMX root, or it can create a user space memory where it points to, which is VMX root. VMX root is quite cool because it actually has a ring 0 and a ring 3, which means that you can actually just port a standard Linux, like any operating system, to it and just swink it a little bit, and actually just will run nicely. And that's actually how KVVM works, and Zen. Basically, Zen is just a Linux operating system running in its things. It's cool. Also, SSM. This is what I was talking about. The TXT I was talking about. This is for as you can see, BIOS. Funnily enough, TXT is actually above this. TXT actually usually, in some implementations, actually has a copy of the BIOS, and it compares a copy of the BIOS with the running BIOS to see if anything's been modified. Little nice security feature, which makes our life so much harder. Hardware manufacturers don't like to be accused for stuffing stuff up, so they do this very intently. So yeah. But what was I saying? Oh yeah, when it boots up, the actual architecture. Please go back. The actual architecture looks like this. It's cool. It moves from rings, basically, but from this it creates this, and this is just the VM. This is just a VM. Quite simple. Yeah. I need to emphasize this thing. It uses instructions to enable this, and basically, I'm pretty sure I need to double check on what I've done. Basically, it creates, in terms of the actual processor, the VMX root is actually just a process, and this is just another fancy process which is directly linked to this one. Makes things fun, but in terms of hardware, these are just processors. x86 does a lot for you. It gives everything like a silver platter. It's basically, you can almost argue x86 is like its own little operating system. It's quite cool. But no. The trusted first, when it boots up, the trusted comes in, BIOS boots into just the standard ring 0. Ring 0, this is just a standard kernel. Then the kernel creates these roots. Then the kernel creates the root. The root then creates the VMX host. Or was it the non-roots? And the non-roots are basically the different virtual machines. For what we wanted, we would have to basically initiate that, make a really dumb VMX root, which just intercepts everything the kernel does. And then the VMX root, non-roots, is just the currently targeted kernel. That was the plan. Emphasize plan. Yeah, but as I said, without this only works if the extensions are enabled. If they're not enabled, none of this does. You have to do it in software, and it's hell. Okay, now time to deal with ARM virtualization. ARM virtualization actually is very different, and it's in some sense, it's more intuitive. It makes a lot more sense, but at other times, it makes life a whole lot harder because it's very simple, but harder. Basically, instead of TNX, it has this trusted zone. Basically, it's actually, funnily enough, it's literally just another kernel. Like, it's a kernel for your kernel. It's a hypervisor for your hypervisor. You're not supposed to use it as a hypervisor, but technically you can actually use EL3 as a hypervisor. As you can see, there's no EL2. Funnily enough, there is now. You can actually have this as another one, EL2, another root thingy. It's fancy, but yeah. Basically, how ARM boots up, unlike x86, where it actually just boots into a normal kernel and the kernel creates this virtual environment, ARM boots up initially in the different executable levels. They're not rings in ARM, they're exception levels. It first initializes in EL3. EL3 is usually the boot code, ROM, blah, blah, blah. It's the highest privilege level. This is where the code, this is similar, you can have this checking the boot code, blah, blah, blah. It's, blah, blah, blah. It checks the boot code. It basically functions exactly, it does the same thing as TXT, but in a slightly different way. Like you can, in here, like nothing here can modify the stuff over here, so this can, you can use this as like a trusted service to verify what's happening over here. Funnily enough, you can actually have, most of the time it's like this that talks. If this doesn't advise, you can actually have it like talk like this. This is actually in terms of Android, where most of the secure, like talking to the verification chips and that stuff happens. Like, yeah. But this is the thing. To initialize EL2, the hypervisor, unlike x86, which can happen at any time, because it's an execution level, it can only be implemented when it's in its execution level. So at startup. After this drops out of EL2, so like an after it drops out of EL2 into EL1, which it sets up. There's no way of getting back to EL2. You can do you can trap it or do a hypervisor call, but if there's nothing in EL2, it just does nothing. It's an illegal instruction, and then this deals with it. So after boot up, there's no way of getting back here, which is a good thing, but it's a bad thing. And unlike x86, EL2 doesn't have a user land. It's just a kernel. It's just this little an exception level, and there's there's no kernel. And you can set this up so that it uses like a general exception, but it's not perfect. So you can't just port a normal Linux hypervisor, a Linux operating system here, and modify it so it becomes a hypervisor. It just doesn't work. Though in later versions, I think ARM version 8.4, they actually implement this so that EL2 can actually just run with a virtual EL0. So that's fine. But the current version, which I'm looking up, is the base V8, ARM V8, 64-bit. Also, this is different if you're looking at 32-bit. Like all of this is different. So yeah, which is Veeam's ARM version 7 below. I don't think there is a hypervisor below version 7 anyway, so for some reason they changed the entire structure in ARM 64-bit version 8. I don't know why. Oh, they probably didn't made it nicer, but yeah. Again, but that's a big issue, as I'll discuss later, because of fragmentation. Reason why there aren't... Because you basically have to create this hypervisor from scratch. There aren't very many ARM hypervisors. Plus, the ARM architecture isn't very, let's say, powerful. Like the instructions per clock cycle is, I think, it's a third of what is on x86, and the actual instructions themselves do less. So yeah, it wouldn't be fair. I think it's a half now, but it's not nearly as good. So people don't really make it, but these are good for like distributed stuff, like heavy distributed workloads. Yeah. So yeah, boot cycle first. But first, the firmware boots it into EL3. EL3 creates the hypervisor, EL3 then either creates itself and this stuff. If it doesn't have any of that, it goes straight to EL2. EL2 can create itself, like it ports it like. Actually, no, EL3 or something over here. Like we can actually have the external. We can have an external chip that actually. Creates the RAM and that stuff, which I will discuss this all later. But like, you have create the RAM, which imports the hypervisor, and then it branches to EL2, EL3, EL2. So yeah, then the EL2 creates the OSs. Technically, we can have EL3 do all this and then just go straight to EL1 and ignore EL2. But yeah, it's nice to do the stepping stones. So yeah, and as you can see, it is very different. So but here's the biggest thing though. This is all enabled by default on ARM. So if you can modify the boot code, you don't have to worry about if the virtualization extensions are enabled or anything. This is just it's just enabled, because in a sense it's like they were like, oh, operating systems, they're cool. How do they work? What if you know what hypervisors? They're operating systems for operating systems. So let's just make another level, which is EL2, which is basically EL1, but like. Again, bigger, just another level below it. And then EL3 was like, but what if we had a hypervisor or like an operating system for our hypervisors? Which is like, so then they made EL3. And it actually gets lower. I think it's up to No, I'm pretty sure EL3 is the last one because this is the trusted zone. But this has actually been heavily modified by version 4. Like there's actually an EL2 and EL3, which somewhat doesn't make sense, but sure. Yeah, cool. Next one. Yes, probably should describe how virtualization. I probably need to describe how virtualization works. Most of the time, it makes things running in EL1 and EL0. Makes things in EL1 thinks it's running on the bare metal, but really it's actually like being swapped out, trapped, and emulates all that type of fancy stuff. It also translates what it thinks the actual hardware addresses to what it translates hardware addresses, virtual hardware addresses, which sounds weird. It's not virtual address spaces, it's virtual hardware addresses to actual hardware addresses, so that you can actually have multiple things mapped to the same hardware or mapped to the same memory. Basically, it's an operating system for operating systems. So it's like it has a page table here. This has its own page table for its apps in itself, and this has a page table for its page table. And to explain what that means, here we go. This is for the mapping of memory, I should emphasize. The operating system on EL1, application on EL0, the guest OS, so EL1 has a translation table for both. It's stored in TBR EL1 and EL0 for the applications. It basically maps their virtual addresses to real addresses. These, so peripherals, flash memory, RAM. But here's the thing, EL2 has a special register called VTTBRO, VTTBRO, basically virtual transition table. It's a transition table in ARM, not page table. Nice. And basically, it's only when you're running as EL2 you can modify this. But basically, it says take these physical addresses and map it to these to actual physical addresses. So it itself doesn't know that it's talking to. Basically, it's another transition. This takes virtual to physical, and this takes physical to another physical. This allows you to have reduce like the RAM space allocated to this, because you can just say, oh yeah, this RAM isn't allocated to you, this can just map to nowhere. And you can segfault and blah blah blah. It's just a virtual map. A hypervisor. The hypervisor has its own transition table via 0 EL2. This is hell because it's actually. I probably should have added the. Go back. Probably should have added the address space breakup, but simply speaking, in 64-bit, the top half is allocated to EL0, EL1, EL0. The bottom half is allocated to EL1. For some reason, in hypervisor mode, because there is no EL0 in hypervisor mode, like there's no user space per se, it only can map in the top half, so it has its own transition table, which only maps in EL0. Yes. Yeah, these are just the page table for the EL2. And these go straight to the actual physical address. You don't go by this thing. You don't go by the virtual address. This is this is the exact same way as what x86 does it. I just thought I'd throw in there just to give you all the information on how transition tables work. Basically, it maps, in the most simplest terms, virtual addresses, it maps as virtual addresses to a physical address. So it looks like it's talking to hardware, but really the actual virtual address, the physical address goes around here and actually talks to this, which then actually taps it to a real physical address. So, yeah, in all intents, it thinks it's talking to a physical address because it thinks it's going straight from here to here, but it's actually going from here. But this actually just goes straight to hardware because they are God modes. But this is one probably I should mention. This is why technically EL3 can't be was a hypervisor for hypervisors, because it doesn't have a transition table. It doesn't have an insertion transition table for EL2. But there is ways around that. Okay, exception handling and this is asynchronous exception handling. Just going to quickly go how a normal operating system does it, and now we're going to quickly explain how a virtual machine does it. Basically, first, an exception occurs in terms of ARM. This is in EL0 application space. It triggers, it executes, I shouldn't say triggers, it executes a software interrupt, or the name changed in 64, but I can't remember at the moment, on the top of my head. Then the flow execution gets redirected to EL1's, which is this vector table. Then the vector table sends it to the correct handler, and then the handler returns. The handler does its fang, and then returns, and then it does an ERET back to 0. I should say that unlike x86, this is actually a lot different because it doesn't actually have a ret instruction. You have to actually you yourself has to put all the, you have to save all the arguments, like your local storage, onto the stack, and then you actually have to move the calling arguments onto the stack itself too. It doesn't do any of it for you. And it makes life a lot harder. Well, it makes it a little more difficult. But this is ARM. It's a reduced instruction set. It's simple. It's like C. It's simple. You have to do more, but you have to do more with it to do the same results. Also, yes, it has the same. It still has a TXT, so yep, can't modify the thing. You can't modify the hypervisor, and in extension, can't modify the, if implemented, can't modify the boot if it has been implemented. And actually, in this case, it's worse, because once it drops out of EL2, there's no way of getting back into this. Unlike x86, where you can just create a virtual machine in the kernel, and then the virtual machine, then you just move everything into that virtual machine. Can't do that on ARM, because the kernel itself can't get into EL2. Different paradigm. Cool. I like it. It's cool. The boot process is dependent on the vendor. Yes, there's no ARM doesn't have a standardized boot process. Like in Intel, most of the time, the Intel management system does the boot process for you. There is still a little bit of UEFI, but like Intel doesn't. Hypervisor implementations is different between the ARM7 and ARM8. Very different. They're completely incompatible. Actually, no. Technically, you can use an ARM7 and an ARM8 processor, but the user land will be ARM7. ARM7 is compatible with ARM8 is compatible with ARM7, but it means everything underneath it has to be written in ARM7 and not ARM8. So basically, you just lose all ARM8's functionality. Very few hypervisors for the platforms. As described before, you can't just port like an operating system. You have to rebuild one from scratch, and it makes it very hard. There's not a heap of documentation about hypervisors for ARM because of, well, one, this. Two, it's just, it can be a little, it's very hard because it's very platform dependent. It's very vendor dependent how they've implemented it because where everything maps to, it doesn't have like a nice. There's not the standards in ARM isn't really there quite yet. It's still a little everywhere. It's like, oh, do you want to map your UR to these locations? Go ahead, just do it. There's no real way of handling I/O or that stuff. Nah, don't need that. Just do what the hell you want. So then you have to create your own drivers and blah blah. Create your own drivers, which means it's not compatible. Not a heap of documentation except from ARM, but that even still is a jumpy. Like it carries a lot of assumptions that you know X and Y and Z. Like even if you follow the documentation perfectly, it doesn't mean anything because of it is still a lot of the parts are still platform dependent. Like I'm going to explain later with the Raspberry Pi. There's just something dumb. Oh, the spoilers, but yeah. And again, whole lot of fragmentation, to platform dependent. Basically, actually, this is the reason why Android's fragmented too. It's goddamn up. So what now? What can I do now? Well, fortunately, there's one ARM processor which ignores everything and does its own and does be a problem child. First things first, what's the biggest issue with Intel? Well, first things first, QBoot. For ARM, no issue at all. Basically, how the boot process on ARM works, it's simply when you turn on the an ARM, the boot process for the Raspberry Pi works. When you first turn on, it actually turns on the GPU. The CPU is still off, and the GPU is Video Core 5, I think. Oh no, I don't think it is. It's a Video Core 5 on the Raspberry Pi 3. Basically, the GPU sets up the environment by first executing stage 1 of the bootloader. This basically all it does is fetch the stage 1. This is run by the GPU. It fetches the initial boot code, which is the bootcode.bin, nicely named, which is executed on the GPU. CPU hasn't started yet, funnily enough, hasn't started, which which is stored on the SD card. Emphasize, stored on the SD card. This doesn't the stage 1 boot code does not at all verify this bootcode.bin. Not one bit. So you can modify this, your heart's content, and it doesn't care. Basically, it reads all this does. It reads the state 2 boot code from the SD card and loads it into the L2 cache, and then runs it. Because the L2 cache is actually shared between the GPU and the CPU. So, lol. Stage 2 bootloader enables SD RAM and loads. Basically, enables the another boot. another loader.bin. For some reason, they broke these up into two, I guess, so that you can update them independently. But these are just both stored on the SD card. All this does is it loads this bitcode.bin from the SD card, and loads this and executes it. And this is the fun one. It loads the start.elf, which is the GPU's firmware. Yeah, we haven't even touched the CPU yet. This is the one which is responsible for setting up the CPU and basically initializing the execution of the kernel. And basically, it loads the kernel into memory. It's a very fun little program. Again, stored on the SD card. It's a little fun program which basically, it reads in this file called config.txt. It sets up, using those parameters, sets up the environment for the ARM. It loads the kernel, and then it it has command. It can take kernel parameters to command line.txt. I actually never used that. Well, didn't see that. Basically, it loads the kernel image into the thing. It sets it executes. Then it finally turns on the ARM by releasing the reset signal on the ARM, and the kernel starts working. So basically, the GPU sets it up. The CPU just then runs the kernel. And you're just thinking to yourself, well, then you just modify start, because you usually like reasonable thinking. When you start to run the execute of the kernel image, a reasonable thing to do is like, why not? You assume it starts in it just starts the kernel in kernel space and just executes it from there, because that's basically the standard. Nah, Broadcom was a little special. They're special kids. But I do have to emphasize this actually doesn't matter, because since you actually have the executable which drops it into EL1, you could have still modified this, because this is basically the boot code which defines it. But Broadcom was a little special, and they're like, yeah, nah. So, that's right. But wait, what about getting into EL2? Well, Broadcom, as I said, Broadcom's a tad special. And what if I told you StartFL actually starts the kernel image in EL2? Just straight up. It's actually... Would you say that's a security issue? Technically, it is. But funnily enough, it's not as much a security issue as the fact that it actually the entire boot code actually comes from a file on your SD card, which can be read by the kernel, the running kernel, just with root privilege, or it could be run by, or it can just be changed by any other system with that had the SD card plugged in as just normal user. Yeah, it's just a file on an SD card. So, yes, technically this is a security flaw, but that's much more of a security flaw. But it's perfect for me, because this eliminates everything. There's no secure boot check, but it didn't matter because we didn't even have to modify the boot code. It does it for us already. We don't have to turn on any extensions because of how ARM is set up. That's not how it works. It's not an extension. It's actually like another level to the execution stage. And basically, yeah. So this is where the fun begins. Because of the fact that this just drops it into EL2 means that I don't have to do. Basically, I just write the kernel. The kernel just copies. At boot time, the kernel can just copy my modified kernel, which, funnily enough, it doesn't even check if the kernel is valid. It literally just looks for a kernel image called kernel.image. So you can make this kernel image anything you want, and then just rename that. Actually, this is even the more fun part. You don't have to even call it kernel.image in the config.txt file. You can just simply just say, no, that's not what the kernel image is called. It's called this, and it will load that. And then you can just have your you can have your malicious EL2 hypervisor copy the kernel.image, and Bob's your uncle. And even funnier fact, with config.txt, you can actually even just state that to initialize boot kernel.image in EL3. So basically, even if there was, even if the kernel.image tried to implement EL, well, even if there was something in EL3, you can just wipe it. It doesn't matter. So basically, you can create with the Raspberry Pi, you can just create you can just create a hypervisor, and it doesn't care. And actually, this is not just ARM in general. This is an issue with Raspberry Pi. I was actually when I was doing my initial research on what hypervisors can run on Pi, basically people who were trying to create this, create a hypervisor, said they just gave up. Just because of, even if you create a hypervisor in ARM, it didn't matter. You can just remove, on the Raspberry Pi, you can just remove it. There's nothing stopping you. Because the trusted zone hasn't been implemented at all. It's just stuffed. So yeah. And actually, I said, using any security mechanisms, why should Broadcom do that? Who needs security? Especially when x86 is just when the Raspberry Pi is used in millions of IoT devices. So yeah, let's dig in and see what damage I can cause on this little device. Also, again, I need to emphasize, the second you have kernel access, you can the second you can actually get just not even kernel access, write access to the boot partition, which is automatically mounted in Linux just as root. So if you can get root access, you can modify this within the device. So if you can get executable on the device, root executable on the device, you can actually just copy your own kernel into this, and Bob's your uncle. You'll create a hypervisor on next boot. So yeah, it's so bad. I love it, but it's so bad. So yeah, let's dig in. Finish recording.